Hi there, and welcome to our lecture on fluids. This is States 3 of Unit 2. So we have 4 key ideas that we're going to be looking at through this lecture. So how do fluids exert pressure? What force makes a rubber duck float in a bathtub? What happens when pressure in a fluid changes? And what affects the speed of a fluid in motion? So let's start looking at that first question. How do fluids exert pressure? So fluids exert pressure even in all directions, and we can define pressure as the amount of force exerted per unit of area of a surface. So for example, when you pump up a bicycle tire, air particles are constantly pushing up against each other against the tire walls. So we've got that internal pressure of the air that's allowing the tires to maintain their shape whenever we ride the bike or just have the tire sitting in place. We can do some calculations dealing with pressure. It can be calculated by dividing the force by the area over which the force is exerted. So we show this equation by pressure equals force divided by area, or P equals F over A. The SI units for pressure is something called a Pascal. The Pascal is the SI unit for pressure. It's equal to the force of 1 Newton exerted over an area of 1 square meter, and we use the symbol capital P lowercase a. And we'll talk about Newton force of newtons more next semester. But just know that Newton is a unit of pressure in this point. Our next topic is buoyant force. So what force makes the rubber duck float in a bathtub? So all fluids exert an upward buoyant force on matter. So buoyant force can be defined as the upward force that keeps an object immersed in or floating on a fluid. So Archimedes came up with this principle that we use to find buoyant force. The buoyant force on an object in a fluid is the upward force equal to the weight of the fluid that the object displaces. So if we've got this container that has this little spout on the side, we fill the water level up just below that spout so that there's no water that's escaping at that point in time. But as soon as we put anything in it, that water is going to be displaced out of that container. So we're lowering this object into this container of water. When this object is completely immersed, or as we're immersing this object, the water is going to be displaced from the larger container into the smaller beaker. And if we take the weight of this water, so we probably wanted to measure the weight of the container empty initially, so that when we have it full of water, we can take the difference of how much it weighs with the water minus the empty weight, because that'll tell us what the weight of this displaced fluid is, which is equal to the buoyant force that's acting on this object that we lowered into this larger container. Some more information. So if we look at the fish in the water or the seagull sitting on the water, the buoyant force is equal to either of those objects' weight, allowing the fish to either stay suspended in the water or the seagull to float on the water. But if we have this shell that we've put in the water and it's sinking, the weight of the shell is greater than the buoyant force. So we could say that this shell has less buoyant force than the weight. If, say we had an object that we put in water and we pushed it down into the water and we let go and it starts to float, then we're going to say the buoyant force on that object is greater than the weight of that object. And that's one example that's kind of missing from this visual, but at least we can get a couple different examples. So an object will float or sink based on that object's density, and this is a topic that we talked about in Unit 1. If an object is less dense than the fluid in which it is placed, it will float. If an object is more dense than the fluid in which it is placed, it will sink. So looking at that information, the density of water is 1 gram per milliliter. So in order for an object to float in water, the density has to be less than 1 gram per milliliter. So in other words, we have to have more volume to the object than we have mass. And here on the second one, for an object to sink, its mass would have to be greater than the volume, so that the relationship, that ratio, switches so the density is greater than 1. So we know that ships are made of steel, but if we just put a block of steel into the water, it's going to sink real fast, sinks like a rock. This is because the block of steel is denser than the water, so the block sinks. So the mass is greater than the volume that we've allowed this brick to, or this block of steel. But if we were to take that same steel and maybe spread it out over a larger volume, as in this ship, so shaping this block into a hollow form, increases the volume occupied by the same mass, and this is going to result in a reduced density because we have increased the overall volume. So the mass may be the same, but the volume which is placed on that body of water is a lot more. So we've got this large volume then that decreases the density, allows the ships to float. So what happens when pressure in a fluid changes? Pascal principle states that a change in pressure at any point in a closed fluid will be transmitted equally to all parts of the fluid. In other words, if the pressure in a container is increased, at any point the pressure increases at all points by the same amount. So mathematically we can say that Pascal's principle is any pressure that we apply is equal to the pressure at all points. So pressure 1 equals pressure 2. So earlier in the video we said pressure equals force divided by area. So Pascal principle can also be expressed by substitution, that a force over one area is equal to a force over a second area. So that's where we get this F1 divided by A1 equals F2 divided by A2. So this is a direct relationship which we can plug into some calculations later and solve for some problems. Hydraulic devices are based on this principle. So in order to lift this automobile, we have to apply a force somewhere. So what we've got here is we've got a small force acting on a small area, and what happens is we then increase the area for this force to be applied for this hydraulic to work. So the pressure is the same on both sides of the enclosed fluid. A small force on the smaller area on the left here produces a much larger force on the larger area on the right. In order for this to work, the plunger on the left has to travel a greater distance over this smaller area for this larger area over a shorter distance to be applied. So thinking about that hydraulic lift, we're going to use Pascal's principle to lift a 9,000 Newton car. If the area of the small piston, A1, equals 10.5 square centimeters, and the area of the large piston, A2, equals 400 square centimeters, what force needs to be exerted on the small piston to lift the car? So we have three values that are given. We have a force that we know that the car is 19,000 newtons. And we also know that the area of the initial piston, so the area is 10.5 square centimeters. We know the area of the second piston is 400 square centimeters. So our question is, how much force do we need to apply on that initial plunger or initial piston to lift that car? So we're going to start with Pascal's principle, substitute the equation for pressure, then rearrange the equation to isolate the unknown values. So we said that pressure 1 is equal to pressure 2. We can rearrange that to say force 1 divided by area 1 is equal to force 2 divided by area 2. Or we can rearrange the equation to solve for what we want. We want to solve for force 1. So we multiply both sides by area 1. So that's where we get this third equation that's shown on this slide. Force 2 times area 1 divided by area 2. So the second half of our equation is still there, but we multiplied area 1 onto the right side, cancel on the left, so we're left with force 1 on the left, which is the variable we want to solve for. So we can plug in our known values. 19,000 newtons is the force of the car, times 10.5 square centimeters, which was area 1, divided by 400 square centimeters, which was area 2. Doing the math, we end up with 500 newtons of force that we have to apply to lift this 19,000 newton car. Alright, next thing we have is fluids in motion. So it affects the speed of a fluid in motion. Fluids will move faster through smaller areas than through larger areas. If the overall flow rate remains constant, fluids also vary in the rate at which they flow. And what we call viscosity depends on particle attraction. And we define viscosity as the resistance of a gas or liquid to flow. So it's any of these items that we categorize as a fluid. So gas or liquid can be considered fluid because they flow. Fluid pressure decreases as speed increases. So we can think about water in a pipe. As the water is moving faster through the pipe, there's less pressure of that fluid on the pipe itself. And we call this Bernoulli's principle. So, thanks for listening.